Mm. Hello friends, hello student. Last class I discussed about the single mode fiber. Based on the mode configuration, there are the two types of the fiber. One is the single mode fiber, another is the multi-mode fiber. For case of the single multi-mode fiber, normally the numerical aperture, critical angle, these are important. For case of the single mode fiber, mainly there is a term mode field diameter. This is the important parameter for if want to uh, send the signal through the single mode fiber. So what is the mode field diameter? Normally, when you can see, suppose this is a core layer of the optical fiber. So normally you can see the light can propagate. It can hit the interface and it can reflect it back from the interface again. It can hit the interface again. It can reflect it back from the interface. And what will happen? And if the another ray will come, suppose another ray, normally single mode fiber, normally one ray is there, but it depends on how the light is incident on the face of the optical fiber. Sometimes it may happen that it hits the interface like this way, so that the some portion of lights are distributed into the interface of the core and cladding. So at top of the so here cladding layer is there, right? So some of the lights are distributed into the cladding layer. Again here also when it hits this surface, again some distributions are like that. Okay, well we know that light has the electromagnetic wave. It has the high frequency signal, low frequency signal, as well as the high frequency signal. Okay, depends on the frequency or wavelength of the signal. Normally the how the light is going to propagate through the optical fiber, it depends. So normally suppose the higher wavelength signal, lower wavelength signal, that may have chance to get the light into the cladding layer. Okay, but in case of the higher wavelength, you cannot see that kind of the distribution in the fiber. So when and the electromagnetic wave, it has the electric field as well as the magnetic field, right? It has electric field and magnetic field. Normally, if you want to represent any kind of the signal or optical signal or any kind of the electromagnetic wave, normally you used to prefer to represent in the form of the electric field. Here in this diagram, you can see this is the core and this is the cladding. Normally, the mode field diameter, what it is? Okay, so it is the defines the characteristics of the single mode fiber. Okay, how the light is propagating through the fiber. These characteristics can be defined by the mode field meter, and it also depends on the wavelength of the signal. That I told that if the different wavelength lines can differently propagate through the fiber. So if sometime it get some distribution, the optical signal may have a chance to propagate into the cladding layer. Okay, so this is the electric field, you can see. So when you see normally in this diagram you can see, so electric field is propagate. Electric field distribution is like that. The electric field intensity distribution is like that. So if you see or to see from the this end of the fiber, you can see there is a spot of the light. Okay, it's coming from the optical fiber. So this is distribution, and if the it is spreaded, electric field is spreaded maximum in the cladding layer, and the cladding layer is minimum less amount of electric field is the core layer. Then you can see the high intensity spot is very less. The diameter of the high intensity is very less, and the diameter of the lower intensity is more. Normally it's happened that the diameter is spreaded. If it's spreaded, the diameter will be like that, intensity is low. So if it's not spread, if it is confined, electric field is confined into the core layer, you can see the small diameter, but it is the high intensity, if you see from the other end of the fiber. So this is called the mode field diameter. If you want to plot the electric field, in this diagram also you can see this electric field distribution is plotted. The R is the center of the core axis, and the radius, you can see radius of the electric field distribution, so it is distributed. So if ray is propagated, if no signals is printed into the cladding layer, then so there will be no distribution of electric field inside the clad layer, only distribution of electric field inside the core layer. right? So this is the two-way diameter, the diameter of the cone layer. So you can see this in this way they can define the distribution. So this width normally, so suppose the electric field is distributed up to this much. Okay, so this width is called as the mode field diameter. How far the electric field is distributed into the cold cladding layer, the total distribution. So how far it is distributed, the area of the distribution of the electric field, that depends the mode field diameter. Okay, the mode field, the electric field diameter normally. You can define the electric field diameter as a E with respect to R, the electric field distributed with respect to distance. So E naught is the maximum field at R is equal to 0 at e to the power minus R square by W square. So W square is the 2 W naught. So normally if we are telling that this is the mode field diameter, so W will be the half of the mode field diameter. Okay, or width of the electric field distribution or spot size. Okay, the mode field the W can define as a electric field diameter of the electric field distribution. Okay, but it is not distributed at a proper way, it is just spreaded. Okay, it is spreaded. So for that the mode field diameter will increase, it's double of the width of the electric field distribution normally or spot size. So here in this right hand side diagram again you can see how can you define the distance of the diameter of the mode field. So normally the maximum intensity it is here only E naught, as it decreases to it is in exponentially decreasing here, and in this side also it is exponentially decreasing here, right? So if it is decreased to e to the power minus 2 into it E naught, okay, this much value. Okay, when it is decreased to this much value, if it is crossed the cone layer, okay, this distance is called the mode field diameter. When the electric field intensity, maximum intensity is decreased to e to the power minus 2 radius of the optical power, that distance is the equivalent to mode field diameter. It is defined here only, the 2W naught. Okay, so there is a formula for this also. So formula is numerical is required, but just for understanding what is the W naught and what is the mode field diameter, so this expression is given and how it's related to electric field. This, for that is, the distribution is given. So, so if the mode field diameter also the distribution of the electric field, that is also depends on the reflective index of the optical fiber. So this is about the mode field by diameter. So the electro optical signal has the electric field. So how the electric field is distributed into the core of the fiber. So if it is spreaded, then it will it is not same as the diameter of the mode field diameter is not same as the core diameter if it is distributed into the cladding layer. So how the total electrical distribution is defined as a mode field diameter. Based on the different wavelength, you can get the different kinds of the distribution of the electric field inside the optical fiber. Let's come to the what are the modes are available in case of the single mode. So these also change some phenomena in single mode optical fiber. Normally, to in the in case of the any kind of what do you mean by the polarization? So polarization means, so again I want to tell that the electromagnetic wave as the electric field and the magnetic field. So how the electric field and magnetic field are oriented. Electric field and magnetic field can be oriented in vertically as well as the horizontally. How the electric field and magnetic fields are oriented for a particular electromagnetic wave or optical signal, that depends the polarization. Suppose in case of the electric field, normally if electric field amplitude is varying along the vertically, so that is called the vertical polarization of which has the electric field along the vertical axis. If the electric field is varying like that horizontally, normally we used to call as a horizontal polarization. Here, the electric field is varying horizontally. The amplitude of the electric field is varying horizontally, right? So this is the vertical polarization. This is the horizontal polarization. So you can give this optical signal into the optical fiber through different way. One is the vertical polarization way, another is the horizontal polarization way. So if the so from that this mode came, the one is the horizontal mode, another is the vertical mode. Okay, if both signals, suppose this is the vertical polarization electromagnetic wave and this is the horizontal polarization electric wave, if both has the same phase, both are propagating as the same phase. Okay, there is the no phase difference. The phase difference means suppose this wave is propagating like this way and this wave is propagating like this way. So these are phase, there is a phase difference. Okay, suppose both are overlap, both amplitude phase are overlap, that means it is not there is no phase difference. So if the two also this vertical and horizontal, these are defined as orthogonal polarization. If some optical signals are propagating through the optical fiber, which has the horizontal mode as well as the vertical mode, and it has the same phase velocity, so this mode is called as a degenerate mode. Okay, this mode is called as a degenerate mode. We used to prefer to send the degenerated mode into the single mode fiber. So there is a one term, that is the effective index, reflective index. So when the light, the polarization of the light, that also change the reflective index of the fiber. Normally, the how the light is propagating, how the light is directing from one media to another media, this everything depends on the material's property like reflective index. Okay, so you can indirectly define that the electric index not only depends on the wavelength, it can also depends on the polarization mode and how which mode the light is propagating through the fiber. So one is the horizontal mode and one is the vertical mode. So suppose if the horizontal mode light is propagating, so then the reflective index will be Nx. Okay, reflective index will be Nx. Okay, Nx, here it will be Ny. If the vertical, so this depends the horizontal direction depends the horizontal mode, and this direction depends the vertical mode. If vertical mode light is propagating through the fiber, then the reflecting index will be Ni. So what I told that the degenerate mode means that both the horizontal polarization mode and the vertical polarization mode should have the same velocity that defines the degenerated mode. So for case of the degenerated mode, that Nx and Ny both should be equal. Okay, if it is not degenerate, then Nx and Ny will be different. Sometimes there is a chance the Nx and Ny both should not be equal, but for case of the degenerated mode, that both the reflecting index will be same as the phase velocity of for both the light are same. Okay, so the two different modes can propagate through the fiber which are orthogonal to each other and which should have the same phase velocity to maintain the Nx is equal to Ny, right? So sometimes it may happen that if the optical fiber, right, optical fiber, so this made up of some crystal and something. You have the crystal and some material. There are the lots of materials are used for fabricating the optical fiber. Okay, if is any asymmetry is there or in imperfection in there in optical fiber, and sometimes some stress or bending happen inside the fiber, then what will happen? There will be no symmetry and this does not maintain the degeneracy mode. Okay, so that time what will happen? Degeneracy mode means suppose that this the vertical polarization wave is like that, horizontal polarization wave is like that. So there will be a phase difference between these two waves. Okay, then what will happen? The Nx will not be Ny. You can in the oppositely also you can depend if some imperfections in there, so reflecting index will not be symmetric in each point of the optical fiber. So when the vertical position light will enter, so it may have the phase velocity will change because of the change in the reflective index, and the vertical position light also the phase velocity of the vertical position light also change the velocity. Okay, so the Nx should not be Ny for case of the non-degeneracy mode, or in if any asymmetry is there. Okay, inside the fiber due to the some imperfection in the fiber or the stress and bending happen inside the fiber, and due to the dispersion I will tell in the coming lecture. Due to the dispersion also, you can see there will have the different velocity which doesn't maintain the degeneracy mode. So then the Nx is not equal to Ny. So due to that, there is another mechanism is called that is called the bioreference. Okay, bioreference. This is the bioreference concept, biofringes concept. So when it happen, is to happen if there is imperfection in the optical fiber, then the effective reflective index will not be same. This term is called the bioreference. The BF is equal to Ny minus Nx, and effective ripple index for horizontal mode and effective ripple index for the vertical mode, both are not same. Here also you can see in this diagram, you can easily see. So the mode X, here it is defined as a fast mode. The vertical mode is defined as a fast mode and the horizontal mode is defined as a slow mode. This I am not going to discuss why it is fast mode and slow mode. Normally the fast mode is the vertical polarization wave going fast, but horizontal polarization wave will going slowly. The velocity is slow as compared to the due to the change in the reflecting index. Due to the change in the reflecting index, normally in anisotropic media, that is called the anisotropic media, there is no imperturbation inside the media. So there is imperturbation inside the media. Then what will happen? The horizontal mode will, the velocity of the horizontal mode will have the less velocity as compared to the vertical mode. So this is called the slow mode and this is called the fast mode. So here you can see both are the same velocity. Once it coming at the other end of the optical fiber, you can see this uh, horizontal polarization light has the different velocity. That's why there is a phase difference. Okay, you can see there is a phase difference. So it's like propagating light this way, one is propagating light this way. Okay, so there is a delta t change in the time. Okay, so this concept is called the birefringence due to anisotropic media. This thing is happen. So birefringence is defined as the effective reflective index between difference between the effective reflective index in horizontal mode and the vertical mode. So birefringence also can define as there is another term B is equal to K naught NY minus NX, where K is the 2 pi by lambda. This is called the free space propagation constant. So in each any wave which velocity is not changing over the time or which amplitude is not changing over the time. So then this phenomena is defined by the free space propagation constant. Okay, so that's why the name comes K is equal to 2 pi by lambda. So next time is the fiber bit length, that is related to birefringence concept only. So here also you can see, suppose here it is different in different concept. You can see here it is slow axis and fast axis. So normally if nx is equal to ny, then what will happen? The both waves should be same. But in case of the anisotropic media, I told that nx not is equal to ny. You can see that this wave, vertical polarization wave and the horizontal polarization wave has the different phase velocity. Okay, you need to, if you need to plot the amplitude graph and the phase graph, you can see the, so suppose at if this instant point it enters into the fiber, the both polar mode, the horizontal mode and the vertical mode has the same velocity. Due to the anisotropic media inside the fiber, you can see the phase of both the wave is changed. So here this little bit increased, here it is increased, and it is so due to the medium only, due to the imperfection only, due to the reflectance index, sometime it will happen. The NX at a certain moment, after certain period of time, it will happen. So at or at some location of the fiber, it may happen that NX is equal to NY. So you can see after certain period of time, the both the phase are equal. So at this moment, you can see at this moment, both the phase are equal. So this distance, you can see this phase graph, both the phase are equal. So this distance, after certain period of time, both phase should be equal. Okay, this length is called the fiber width length. Normally it used to happen integral of the multiple of 2 pi. Okay, multiple of 2 pi it used to happen. After 2 pi multiple, it used to happen that both the phase velocity of the both mode will be same. Okay, so this length, after a what period of time, the both the phase will be the same. So this length is called the beating. This is the beats, both beats each other. Okay, this concept is called the fiber bit length. So fiber bit length, that's related to birefringence concept. LP is equal to 2 pi k bf. K is the propagation constant, right? So I think it is clear. The phase difference will be the different when both the waver enters into the fiber, but after certain period of time, both phase will be the same. So the distance defined the how after a certain period, after how much crossing the distance, after a certain period of time, both the phase will be same and reproduce the same signal. Okay, you can also depend on both the phase polarization can reproduce. Okay, so this length is called the fiber bit length. So when the phase difference between two modes is integral of 2 pi, the two modes will be at this point and the input polarization will reproduce. So both same polarization you can see, like a input mode. Okay, this concept is the fiber bit length. So the fiber bit length and the mode field diameter by reference concept, these three concepts are main parameter if you want to define in a single mode fiber. Okay. Next come to the multi-mode fiber. So multi-mode fiber know that multiple signals are propagating through the fiber. For that the numerical aperture is the main important. So in case of the single mode fiber, core is the small as compared to the multi-mode fiber. For case of the multi-mode fiber, core diameter should be large as compared to the single mode fiber, right? So now number of multiple number of signals propagating through the fiber, that's why it is defined as a multiple mode. And this is also because different kinds of the signal has the different wavelength. So based on the different wavelength and the reflecting index, the light the how the light is propagating through the fiber, it also change the phenomena. Multi-mode fiber normally it can give the 10 millisbit per second to 10 gigabit per second data over a 600 meter. Normally it is used for the short distance communication, because here in case of the multi-mode fiber, different signals are propagating. Okay, different signals are propagating. It can create a dispersion. This I will discuss in the next coming lecture. So the dispersion causes the losses in the fiber optical power. Okay, so that's why for longer distance you can multi-mode fiber is not suitable, and it also gives the less bandwidth for multi-mode fiber. So normally the multi-mode fiber, the mode I have already discussed, the formula I have already discussed. How many number of modes are available in case of the multi-mode fiber, that depends on the diameter of the multi-mode fiber, wavelength of the optical signal, and the numerical aperture of the optical signal. Because how numerical aperture defines the light gathering capability. Okay, so that defines the mode of the multi-mode fiber. There are some advantages. Normally, you can easily launch the light through the LEDs, because its diameter is large, right? So that's why using the LED is one kind of the light source. Using LED, you can easily launch the light into the multi-mode fiber, and the fabrication is also easy for multi-mode fiber because the diameter is less. But in case of the and it is also less costly, and we are using the LED also less expensive for case of the multi-mode fiber. With respect to the reflecting index, you can define the optical fiber in two types. One is the step index fiber, and another is the gradient index fiber. For case of the single mode, normally used to prefer the step index, but for because the single in the single mode only the single light is propagating and diameter is also less. So for single mode, used to prefer the step index. For multi mode, we can design the step index as well as the gradient index. So in previous lectures, I have discussed about the meridional ray and the skew ray. That those kinds of the ray depends on the step index as well as the gradient index fiber. Now you can see in this diagram, in case of the step index, the reflecting index of the core is constant, like suppose N1, and the reflecting index of the cladding layer is different, that is N2. Okay, the constant reflecting index inside the core layer and constant reflecting index outside the core layer, cladding layer. The core size is normally depends on the 8 to 12 micrometer in case of the single mode step index fiber. Based on the various application, the various modes are used. Normally, television, that is the for long distance communication, you used to prefer the single mode step index fiber. So there are some advantages. We know that the single mode there is only one signal is propagating, so there will be the no dispersion, and so that means low loss inside the, and it can use for the long distance communication. This I have already discussed. And you can see that if different modes are propagating through the fiber, so this way the lights can propagating through the fiber. There are the different modes in the multi-mode fiber. Now if you compare the step index multi-mode fiber and the gradient index multi-mode fiber, for case of the step index, the diameter is, both diameters are larger than the single mode fiber, but if you compare the multi-mode fiber step index and gradient index, the diameter of the step index is larger than the diameter of the gradient index. You can see the diameter range here, And what is the gradedness? I'll tell. The multimode step index, you can see the diameter is large, the concept is same. The step index means the reflecting index inside the core is constant, and outside the core is also constant. But for multimode, the multiple rays are propagating through the fiber. It's the range of the core diameter and the cladding diameter. As the if the diameter is large, then it is easy to fabricate. Okay. This you can see the zigzag path is following. So this path is called, the different rays are propagating, that the zigzag path is following for case of the step index. Now for case of the graded index, right? So for case of the graded index, normally what happen, and the reflecting index you can see gradually changing inside the core or layer only. Okay, reflecting index is not constant; it's gradually changing over the distance between from the axis to core layer, core and cladding interface. Here also you can see the reflecting index is continuously gradually decreasing a distance bit from the center to interface of the core and cladding, right? So it is that means you need to design the signal such a way that the reflecting index will vary inside the core layer. So here that means the fabrication is difficult for that case, but you can easily launch, but it's not difficult as compared to the single mode fiber, right? In case of the multi-mode step index, you can see different way for light is propagating. Different ray are reaching at the interface at the other side of the optical fiber at different point. Okay, but in case of the gradient index, you can see in this way helical shape, skew ray. It follows the skew ray. Okay, it follows the skew ray, and if you see the other end of the fiber, all the rays are uh, reaching at the same time the other end of the fiber. So it will give the less dispersion or less loss of the signal, optical signal. You can see some which signals are touching at the interface of the core and cladding. This is called the longer ray, and this is called the, it's not touching, it's near to the axis. This is called the shorter ray. So though those rays are following the longer distance, and these rays are following the shortened distance, but at the end, and then all the rays are reaching at the same time, because their velocities are different. That's why they are reaching the interface at the other end at the same time. Okay, so that means it will give the less loss inside the fiber. Okay, this thing is mentioned less loss and difficult to launch. It is easy to launch light because the diameter is large. Okay, but difficult to integrate, the fabricate.